Hello, students. This week, we'll continue on chemistry, the chemistry that's important to understand biology. So, Chemistry of Life, Chapter 2. I won't narrate this whole PowerPoint or lecture. Rather, I'll go through small sections. And of course, anytime you wish for me to create a micro lecture on any of the topics for the lecture, the PowerPoint, you're welcome to send me a message using the Canvas inbox. So let's get started. Life is composed of matter. And being that this is biology, the study of life, we cannot escape studying about what makes up matter. So we start with the atom. Remember the hierarchy of life. And so with the hierarchy of life, we start with non-living particles. We go down to the level of the atom, which is basic unit of matter. So the cell, as you recall from chapter 1, is a basic unit of life, the fundamental unit of life, the one entity that displays all the characteristics of living organisms to be considered living. The cell is the building block of life, of organisms, multicellular organisms like ourselves. The atom is the building block of matter. And what is matter? Okay, so matter is anything that takes up space and has mass. Everything is matter. I like to make the joke that you matter, of course, and I always get a smile or two, so maybe I got a smile or two out of 120 students in this class, so that makes my day. So we go on. Matter, objects that make up space and have mass. Molecules are two or more atoms, and then we have compounds, etc. Okay, these atoms make up what we know as elements, and elements cannot be broken down into any other substance. So elements are made up of just one type of atom. So we go down to understanding the atom and the anatomy of the atom. Right, the anatomy of the atom. Now, a lot of you are engineers, so just keep in mind that you'll probably have to take a lot more chemistry than I present in this PowerPoint. We just want to understand enough so we could understand how life is being built up, or the hierarchy of life. Okay, so if you read over those 400 posts for the introductions, you know there are a lot of engineers in this class. So you might have already taken chemistry, and this is our review for you. But for those of you who haven't, freshmen that you're starting off and never took chemistry in high school, let's go over the anatomy of the atom. So the anatomy of the atom's made up of 3 subatomic particles. So they're smaller than the atom. They make up the atom. And these particles are called, in the center of the atom, we call the nucleus, we have protons. And protons here is denoted by the letter P as a positive sign. Also located in the nucleus, we have neutrons. Neutrons are denoted by the letter N. Surrounding the nucleus in these orbits, or orbital shells we call them, we have electrons that are shown by the E with a negative charge to it. So the charges, the plus, the negative, are assigned to positive for protons, negative for electrons. This is the basic anatomy of the atom. There are 92 naturally occurring elements. These elements are listed in what's known as a periodic table of elements. So they are arranged such that they're according to characteristics, similar characteristics and properties. So if we look starting at group 1, they are the alkali metals, and so that includes lithium, sodium, potassium, etc. I know that since they're in group 1, in the outermost shell, the orbital shell, they only have 1 electron. That's their valence shell, 1 electron. Group 2, beryllium, magnesium, calcium, being that they're in group 2, they have 2 electrons in the outermost valence shell. These ones are known as the alkaline earth metals. Then we go to the center here where we have these in yellow colored area. These are the transitional metals. We go to the right, and then we have the purple area with other nonmetals, the whitish area with nonmetals, and then we have the seventh column and the eighth group. So if group 1 has one electron shell, one electron in its valence shell, group 2 has 2, group 3 has 3, etc. Carbon, which is located in group 4, group 4, it has 4 valence electrons in its valence shell. And then if we go all the way to group 7, these have 7 electrons in its valence shell. So you can see the pattern here of their characteristics and how they're arranged, and that actually will help you know how they form bonds together. In group 8, we have the noble gases. So noble gases means that they are stable. Their valence shell, the outermost shell, is completely full. They follow the octet rule. And so they want to be left alone. Nobility, right? They want to be left alone. They're happy. They have everything they need. So all the other ones preceding this column are reactive. They haven't met the octet rule, so they're going to be able to form chemical bonds. So this is a periodic table. All the elements are listed by their initial, their symbol, and they have the atomic number. The atomic number matches the number of protons. Most of the time, the number of protons matches the number of neutrons, and we'll see that that's not always the case when we have isotopes. It has the name written out in the bottom, and then under the atomic symbol, we have the atomic mass. So here we have a pictorial representation of what I was mentioning with the periodic table. When we start with group 1, we have here in H, that's helium, we have one electron in its first electron shell or orbital shell. It's actually the only orbital shell it has. It only has one electron, but the first orbital shell could occupy 2 electrons. This is group 1, period 2, the second row. We have lithium. Lithium has 2 electrons in its first shell, and it has 1 electron in its second orbital shell. So the last orbital shell, the second orbital shell, only has 1 electron. Now there could be up to 8 electrons that could occupy this space, this orbital shell. This orbital shell, the outermost, is called the valence electron. If you go down to group 4, group 4, carbon has 4 electrons as previously mentioned. So to get to 8, it could attain 4 more electrons. Group 7 has 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. 7 electrons. So in order to meet the octet rule, it wants to gain an electron. It would be easier to gain 1 electron than to lose 7 electrons. And then group 8, the noble gases, the octet rule is complete. The valence shell is filled, so they're stable elements. So we go back to group 1. It's easier to lose an electron or to gain one for hydrogen. Hydrogen. Helium is in group 8. So for hydrogen, it could easily lose an electron or gain an electron. But for period 2, second row, there's 1 electron. Well, it'll be easier to lose that 1 electron than to gain 7 electrons. If we go to fluoride, fluorine, we have 7 electrons, so it'll be easier to gain an electron than to lose 7 electrons. And likewise for sodium. Sodium will be easier to lose 1 electron than to gain 7 electrons. Chlorine will be easier to gain an electron than to lose 7 electrons. So here we could see the pattern of potential chemical bonds forming. And so this is fundamental for you to understand in order for you to move on and understand chemical bonds. Life, or let's personalize it and make it relevant. We are made up of mostly 4 atoms, okay, 4 elements. These 4 elements are oxygen, 65%, carbon dioxide, 18%, hydrogen, 10%, and nitrogen, 3%. If we look at oxygen, 65%, and hydrogen, 10%, those are the 2 most common, right? We get water. So, and you've all heard that we're mostly made up of water, right? We're between 65, 85% water. It varies by the different cells we're talking about. So we are made up of these 4 elements: oxygen, carbon, hydrogen, nitrogen, and 18% carbon, and anything that has the basis for carbon as a building block is considered organic. So the carbon presence. If we look at atmosphere, Earth's crust, we see that carbon's trace for both of them, and then the distribution of the other elements as well. So even though we're made up of mostly the 4 elements, carbon, hydrogen, oxygen, nitrogen, it doesn't mean that we don't have other elements that make us up. It just means that the other ones are in a very small amount. So we have calcium to 1.5%. So in comparison to 65%, 1.5 seems very low. However, calcium is very important. You know, your mom told you drink milk because it has a lot of calcium, or green vegetables like spinach and kale because of the calcium. And calcium is so important because it is part of the formation of bone, right? It's important for building strong bones and teeth. It's also involved with um, muscular contractions, muscle contractions. So those are just a couple of examples of the importance of calcium in the body. Likewise for phosphorus. Phosphorus makes up a major component of our DNA molecule. That's important. Potassium, sulfur, sodium, chloride, and magnesium are also in lower amounts, but they're very important um, elements. Now, some other elements are called trace elements. Again, this is because of the amount that's needed, less than 0.01%. However, if we look down the list, we see that some of these are quite important elements. We have iodine, we have iron. Iron is a component of your red blood cells. We need it for red blood cell formation. Red blood cells are the most abundant cells in the human body. Their function is to carry oxygen, right? We saw that in chapter 1. Their function, their structure lends to function. And in order for it to carry its function, and we'll see this a little bit more clearly later on in the semester, they need to have that iron in the center of the protein that allows for the red blood cell to carry oxygen, like hemoglobin. And so iron, even though you need it in less than 0.01%, very important for all of us, we have the potential of being anemic due to a low iron consumption or low iron in our body. And that would reduce the ability of red blood cell formation, which would lead to fatigue and lethargy, overall symptoms of low iron, which is something that a lot of women would suffer from, particularly women, but men could also suffer from iron deficiency anemia. So that's just one example. There's also iodine. Go to the next slide. Iodine deficiency causes a swelling of a gland called the thyroid gland. And the thyroid gland is an endocrine organ. So it produces hormones. These hormones allow you to it regulates your metabolism, it regulates your growth. So this gland located in your neck underneath your Adam's apple for men. So if you feel your Adam's apple right below it, you could palpate your thyroid. If you have an iodine deficiency, you will your thyroid gland will swell up, and so that's what's happening here, and that's known as goiter. And we don't have that problem here so much in America, highly developed country, because iodine is actually added to our salt, and we need a trace amount. Well, we get that amount through already the food that we consume. Fluoride is another trace element that's added to the drinking water and dental products. And so these are trace elements, but they're important. They have a function in the human body. Right. So according to your textbook, water makes up 67% of the human body. Now, I did have in the topic exploration quiz that it makes up 65 to 85% of the human body. And that's mostly because different cells actually have different water content. And so between 670, 65, 80, you're within the same ballpark. Okay, so point being, water is essential to life. Okay, most critical molecule for life on Earth. And it's the properties of water that you just went through in the PowerPoint that make it so critical for life. It is a polar molecule. It can form hydrogen bonds. All right, so just looking at one water molecule, oxygen with two hydrogens, recall that oxygen is more electronegative than hydrogen, so it pulls the electrons more to itself than to hydrogen. This creates this polarity with the hydrogens being slightly positive and the oxygen being slightly negative. They have that polar covalent bond. Since that's a characteristic of one water molecule, then each of the water molecules are attracted to each other, opposites attract. And so the slightly negative oxygen is attracted to slightly positive hydrogens of other water molecules. And we have what's known as the hydrogen bond forming between water molecules. And you could see that here. It is these properties that allow water to stick with water and stick with itself that gives it the properties of water. These properties of water include water's universal solvent, water's less dense as a solid, water moderates temperatures, and water is highly cohesive. So water's power as a solvent. Being that it's characteristic, it has these hydrogen bonds, it has this polarity, then it's going to be attracted to other polar molecules. And these molecules are going to be known as hydrophilic molecules. Hydro meaning water, referring to water, and phileo means to like. So these hydrophilic molecules, you could probably think of a few examples like salt and sugar. It easily dissolves in water, allows for water to act as the universal solvent. So here we have an example of table salt, so sodium chloride mixed with water. And so because of the polarity and the ionic uh, bond between sodium and chloride, the water molecules shown in the green, I'm sorry, in the red with white, the water molecules will form a hydration sphere around each of the ionic or cations and ions of the sodium chloride molecule. This forms the solution where the solute is a compound dissolved in the solution. The solvent is the water, and what is created is a homogeneous mixture of two or more kinds of molecules. In this case, the water with the sodium and the chloride. Water is less dense as solid. So because of water solid form, ice, and it's less dense than its liquid form, it forms a lattice network above the water in this ice formation that allows life to flourish underneath the ice. Water temperature moderation. So water has a high heat capacity and it's able to retain heat. Okay, heat is a form of energy. So water acts to moderate temperature. Whether we're talking about on a global scale, the earth acts as a heat buffer. The water of the earth, I should say, acts as the heat buffer. Water will also have a role in cooling our body. Remember, homeostasis is maintaining a steady environment. So in our body, our core temperature is 37 degrees Celsius, 98.6 Fahrenheit. When it gets very hot, what happens? You start sweating. So that is evaporation, and it takes a lot of energy to actually break the hydrogen bonds holding water together. So that energy, once it's broken and the hydrogen bonds are broken, then water evaporates and has taken some of that heat off of you to cool you down. It's the same principle applied on a global scale with the oceans. They act as a heat buffer, stabilizing the Earth's atmosphere. Water's cohesive property. Water likes water, okay? So it has a high degree of cohesion. And this cohesion allows water to stick to water. That hydrogen bonding will allow it to rise to the top of a 100-foot tree. This cohesion will allow a surface tension to create it on the surface of water where insects like this water strider or Jesus insect is able to walk on water. And it allows for us to also, when we're filling up a glass of water, you see it that, as your textbook mentioned it, dome-shaped overflow of the glass. If you overflowed it, this is all just water sticking to water. Okay, so this is a property that allows for that tree to get the water where it needs to be, for water to form that surface tension, and it withstands being disrupted. And so that's water's cohesive. The pH of the solution indicates acidity or alkalinity. So what is acidity or alkalinity? pH is a measurement of a substance's hydrogen ion concentration. So here we have hydrogen on the left, hydroxide ions on the right. The increase in hydrogen ions in a solution will determine the pH of a solution. So in this case, the more hydrogen ions you have acidic substances. The more hydroxide ions you have, the more basic substances. pH is measured on a scale called the pH scale. It goes from 0 to 14. Right down the middle is pH 7, that's pure water. Pure water has an equal concentration of hydrogen ions and hydroxide ions, so that's neutral solution. Anything below 7 is acidic, and anything above 7 is alkaline or basic. So basic solution, above 7, acidic solution, in below 7. So what is acidic? We have grapefruit juice, that would be about a 3. Lemon juice, we have about a 2. Stomach acid is about a 2. So that helps with digestion, which we'll talk about next week for week 3 lecture material. Black coffee is it's acidic, not as acidic as lemon juice, but it is acidic. And so that's just saying it has more concentration of hydrogen ions. So what is basic? We have human blood is slightly basic. It's between 7.35 and 7.45. A very exact range, small, narrow range that's slightly alkaline or basic. Milk of magnesia is basic, household ammonia, household bleach, and down to the very extreme basic or alkaline, we have oven cleaner. So this is a pH scale. Applying pH to our cells, making it relevant, we have living things function best at a near neutral pH. So for our body, going down the esophagus, it's going to, starting with our mouth, right? We're going to have a near neutral pH down to esophagus. But you've heard that the stomach has acid, right? You probably have tasted it before. And so that's near pH of 2, 1.5 to 2. That helps with digestion process. But if we go elsewhere in the digestive system, we go more of a neutral pH. We could test pH of the foods that we ingest that I just showed you. For example, we have lemon, which is like about a pH of 2. And at home, you might want to try this at home. If you have purple cabbage, it forms this, if you boiled it down, you have this purple solution. So we could test the pH of some of our substances by adding purple cabbage, the liquid of purple cabbage, to whatever you want to test pH for. We know that lemon juice is a pH of 2, so if I add this purple cabbage juice to the lemon, this should turn a pink color because that's going to indicate that it is acidic. The cabbage juice is acting as a pH indicator, just like litmus paper you might have used in lab, or you might have heard of litmus paper. So it acts as a pH indicator. It thinks if it detects something acidic, it turns the solution pink. If it turns blue, like a light turquoise blue, then the solution is basic. This is lemon juice. So to test its pH, we just add the cabbage juice and see if it turns pink. So we know that lemon juice is in fact acidic. Okay, so pH scale, concentration of hydrogen ions, very relevant because our blood needs to be maintained at 7.35 to 7.45 pH, right? That's a variable that must be maintained if our body to be in homeostasis, a stable, steady state. The pH of the stomach needs to be a low pH because of its function and digestion, breaking down macromolecules. So different parts of the body, different variations in pH, but those pH levels must be maintained.